And so we're going to build on that today here with the last talk in the soils session before we get into water. So I'll be talking about fertilizer and soil amendment selection and use in Utah soils. So we're going to take all these building blocks and really put them together in kind of an applied way. For those of you who don't know me, my name is Melanie Stock, and I am our Extension Urban and Small Farm Specialist, and I'm a soil scientist by training. So, all right, let's go ahead. I need to just close out this poll, or there we go. Okay. All right. So so I'll be talking about three main things here in the next 25 minutes or so. I want to start off talking a little bit more about the core concepts of soil fertility. I think it's just interesting to know. It also helps us really critically think about what we're adding to the soil, as well as just appreciate everything that soil is doing for plants. And then from that, we're going to talk about different fertilizers and amendments that can be used and the selection of those. And then finally, we'll finish up calculating the nutrients that nutrient rates to add to the soils to maintain sustainable management practices. Now, I want to start off with some definitions here because we tend to throw these words around a lot. So any kind of product that's intended to supply plant nutrients always have three numbers on the package, and they're always in the same order. It's nitrogen, phosphorus, and potassium. So NPK. So those are the three primary nutrient macronutrients that we're managing in the soil. We also tend to either call things fertilizers or amendments, and so I just want to define that here, that if the three numbers on the bag, the NPK, add up to more than 24, it's considered a fertilizer technically. If it's less than, then it's an amendment. And so I've got some examples of fertilizers here on the screen. I've got more coming. And I just want to show that our fertilizer and amendment producers spend a lot of money on marketing and can have very beautiful bags and boxes. And so you might have to hunt around a little bit, but those three numbers will be on there somewhere. So here's an example: bone meal to start with. The first one is 115.0. The other one is 315.0. And I just show both of those that to say that even though it's called the same thing, there are some differences by brand. Dr. Earth, this one's hard to find, but there's that 463 right on there. Chicken manure, urea, and there's two examples of urea. I think the one is 45.00, whereas the last one here is 46.00. And so the first thing I just encourage you to do is to, when you're selecting a fertilizer, we're going to talk a lot about this, but just a consideration of what the guaranteed analysis is. And so what this means, so for example, with this chicken manure, 3% of the total of what's in the bag is nitrogen, okay? And so those are some things to consider. Now I've got one more slide of definitions and we'll move on. So I want to define organic because we use the word organic a lot, and it can mean really different things. So organic matter, we talked a lot about that this morning if you were in the microfarm session, but organic matter is, at the most simple definition, the remains of decomposed plants and animals in the soil. They lived, they died, they became part of the soil, and that's what gives topsoil its dark color. So here's a picture. I'm holding a soil with a really high organic matter content, so it's quite black in color. Then there's certified organic, and this is getting at the actual USDA program that ensures certain farming practices or standards are met, whether that's produce being sold or if you're looking for an organic fertilizer or amendment, it has this OMRI label on it. And then finally, there's the term organic as in organic chemistry, which just means that there's carbon in it. Something that it's typically from something that was once alive. So if you grew a cover crop, maybe clover, for example, and it's decomposing, there's nitrogen in it that's going to get released to the soil, we would consider it organically bound because it's bound to carbon. So, all right, let's move on. So actual nutrients in the soil, there's 17 essential nutrients that all plants need to survive. 14 of those are mineral nutrients. So the three non-mineral nutrients would be oxygen, hydrogen, and carbon. So that's getting at water and air, and so forth. And then the other 14 essential mineral nutrients are all in the soil. And so we divide those into two categories, macronutrients and micronutrients. Macro means big, plants need those in larger quantities as opposed to our micronutrients. Within these macronutrients, nitrogen, phosphorus, and potassium, those are our primary macronutrients because of all mineral nutrients, those are the ones that the plants need the most, particularly nitrogen. So it's just really amazing to kind of step back. I know a lot of us have heard this before, but just to really appreciate what the soil is doing for plants and just the complex chemistry that's happening in that soil by managing all of these nutrients. And so I have this slide. These slides will be available for you to reference in the future if you want, but I won't read through all of these here, but I just wanted to put up a quick list of the different mineral nutrients because it's just amazing what the role of each one in plants. And so a lot of complexity happening here. But taking it back to soil management, I've listed some macro and micronutrients that we tend to have to manage more than others here on the list. And so I've got the nutrient name, and then I also have its chemical form or its elemental form. This is its plant available form, I should specify. So it doesn't really matter what fertilizer we're adding to the soil or what amendment. In the end, it has to break down into these plant available forms in order for a plant to be able to use it. And these are the forms here, and this is how you would say that out loud. And so I just want to point out what these all have in common is they all have a charge associated with them. Right. So that's important because it has a lot to do with how they're held in the soil. So general nutrient retention in the soil, this was touched on a bit, but I'll just go through it quickly. Here I have a diagram. This is my really bad picture of a clay particle. Sand and silt are generally rounded particles in the soil, but clay kind of has this layered structure to it. It's almost like if you have your notebook, you've got a bunch of layers of paper in it. Each one of those layers would be like a layer in clay. And clay has this negative charge to it, and that's what lets it attract water and nutrients. So the positive side of water and then cations or plant nutrients that have a positive charge. Kind of like, I don't know if you all liked playing with magnets as a kid, I did, but if you have the positive end of a magnet and a negative end, you put them together, they really want to stick together. If you have two positive sides of the magnet, they want to repel. If you have two negative sides, they also want to repel. And so similar thing is happening here. So clay is negatively charged, therefore it really wants to hang on to positively charged nutrients. Organic matter, so here's a schematic showing a couple clay particles. They've got a negative surface charge. When you have organic matter in your soils, one of the benefits of it is that it actually has positive and negative charges to it, which means that it can then help hold elements with both and atoms with both positive and negative charges. And so that's kind of getting at some of the importance of organic matter, not only because it comes with nutrients, but it can also help hold them in the soil. Now, these nutrients are being stored in the soil, but one of the really wonderful things that soil does is it acts as this wonderful bank. It's storing these nutrients and it stores them in kind of these different forms. So a soluble nutrient is a nutrient that's dissolved in the soil water and a plant can access it immediately. So if I'm thinking of soil like a bank, I like to think of soluble nutrients in the soil as a checking account. It's completely free. The plant can take what it wants when it wants. It's available. The soil also has insoluble nutrients that cannot be accessed by plants. So I kind of think of this as maybe like more of a custodial account or some kind of savings account that the soil has a lot of backup and it can make some of these nutrients available when the soil water gets depleted. Some of those soluble nutrients get depleted. Nutrients without a charge are often organically bound or insoluble, aka not plant available. So they must first decompose or mineralize to become available in the soil. Now, there's also the last type of storage of nutrients in the soil is actually embedded into the crystalline structure of the soil, and that will not be available to a plant in its lifetime. So I like to think of that as a very, very protected trust account for the soil. So there's all these places that nutrients can be held in the soil. These are the two that I really want us to think about, the ones that are soluble, immediately available, and then the ones that could become available in the future. Now, similarly, there's a lot of terms. If you were to turn around the bag of fertilizer or an amendment and take a look at the fine print, there's more terms to kind of take a look at. So terms that say available or soluble nutrients, those are available right away to the plant. Insoluble, organically bound, slow release, those are not available right away. They have to be broken down first. And so those are some considerations to think about when you're selecting a fertilizer. So here I've got an example of fish emulsion, fish fertilizer, which is 5-1-1, so 5% nitrogen, 1% phosphorus and potassium. If you turn the bottle around, you'll see the fine print. Total nitrogen is 5%. 0.5% of that is ammoniacal nitrogen. That's also a form of soluble nitrogen. It's readily available. 3.75% is other water soluble nitrogen. And then 0.75% is water insoluble nitrogen. So that won't be available to the plants right away. And you can see that all of the phosphate and potash is available right away. So here's that Dr. Earth from a previous slide. On the front of the bag, I think it said 463. The total nitrogen is 4%. But of that, 4% of it is water insoluble nitrogen, which means it's not going to be available to the plant right away. It's going to need some time to break down. That's especially important to think about as you select fertilizers for the beginning of the season and making sure that there's sufficient nutrients in place for the plants. Let's see, feather meal. This is another popular one, especially in organic situations. Total nitrogen, 12%. 12% of it is water insoluble. And I've got one more, green sand. I think it's 001, so it's a potassium only source. This stuff takes forever to break down. Yeah, so for soluble nutrients that are available right away, those can last weeks to months. It really depends on your situation. You might consider doing a split application, so adding some fertilizer prior to planting and then some in mid-season, because it is more difficult to keep those soluble nutrients in place. And I'm especially looking at nitrogen here. When we talked about the charges on the different atoms for the plant nutrients, nitrogen, often, nitrates, for example, come with a negative charge. They're harder to hold in the soil. And so adding those as a split application can be a good way to go. And then thinking about if you're going to be using forms that are insoluble, when that's being added and when that's going to be available. So maybe adding blood meal or feather meal in the beginning of the season for later on in the season, but it certainly wouldn't help things at the very beginning. I wanted to touch on compost here too, and manures. They both have soluble and insoluble nutrients. So when those are applied to the soils, so for compost in the first year, about 5 to 10% of the nitrogen is available. Most of the phosphorus and potassium is released. And then you also get a credit, about 10%, especially thinking about manure here, in subsequent years. So whatever you're adding this year, it's going to have an effect in the future too. So I always want to have the jazz hands, and then I quickly get sick of the theme here. But so I just want to give kind of a ballpark estimate about when these nutrients are released. What's the timing of that? So soluble nutrients, when those are added through fertilizers and amendments, are available right away, and they can last weeks to months depending on practices and the source. Consider split applications. Insoluble take longer to be available, and so forth with compost and manure. So those stick around in the soil, and some is available right away and some is available later on. So now let's talk a little bit about application rates. The first thing to do always is to start with a soil test. Why? This is really how we monitor nutrients in the soil. It's a good way for us to check in on our salinity and pH. As soil scientists, we say that for annual cropping systems, soil should be tested every year. For perennials, every couple years. And I don't know if my standards have just gone down a lot, but I say if you can just test it once, just to start off, find out what your baseline is. And if you can test it somewhat regularly every year or every couple years, that would be ideal, because that's really how we know how much to add. You just can't tell by looking at the soil. But once you start soil testing and adapting your management practices, it becomes a lot more predictable to work with. So I recommend getting your soil tested for phosphorus, potassium, salinity, and pH at least when you're thinking about application. Knowing your soil texture is also important, and we're actually going to have a presentation in the cut flowers session. One of my grad students is going to walk people through how to texture your soil. You can also get it sent into the lab for an exact analysis on what the texture is, because all of this really influences when we're adding fertilizer, how much, how we're irrigating, and so forth. So these are great things to know about your soil when you're trying to determine how much fertilizer and amendments to add and when. And it also is important for diagnosing problems, because many of the visual symptoms that plants show can look the same across problems. The best time to soil sample is prior to planting, especially in new landscapes. So spring is a great time. Fall is also a good time that you can soil sample. It gives you a lot more time to plan over winter for the spring. And then if you can resample every couple of years, it really, really helps inform management and make things sustainable over time. I have this little fact sheet, Urban Garden Soils Testing and Management, that we came out with, and it talks about how to zone your gardens or micro farms for soil testing, how to take those samples and send them in. I can add that link to the Q&A later if that's of interest. So these are the things to get started in with your soil test. We don't typically test for nitrogen every year, and that's because nitrogen is just typically needed to be added every year. So we have this handy dandy kind of rule of thumb, and it depends, the amount of nitrogen to add every year depends on what crops you're growing. So I've got vegetable examples here on the slide. And so they're categorized by low, medium, and high intensity vegetables. So low intensity would be peas and beans, about 1 to 2 pounds of nitrogen per 1,000 square feet. And then that works its way on up to high intensity vegetables, which is about 4 to 6 pounds of nitrogen per 100,000 square feet. So between this rule of thumb and doing a soil test to find out how much P and K are actually needed, a lot of people find that they've actually accumulated high levels of P and K and they don't need to add any more. And again, a negative of adding more nutrients than you need is that you can increase salinity, particularly with potassium. But with those tools, you can truly do precision agriculture right on your small farm or garden. Now, say you did a soil test, you figured out what you needed for phosphorus and potassium, you know what vegetables you're going to be growing. Maybe you're grouping them when you're planting the garden by their fertilizer intensity to make fertilizer applications a bit more efficient. Then the next step is to select a fertilizer or amendment. Again, it should be based on the soil test itself and figuring out what nutrients do you actually need. Just nitrogen, or do you need a complete fertilizer, one that has NP and K? And then also considering the cost factor of the different fertilizers. So sources of nutrients, really the world is your oyster for when it comes to fertilizers and amendments, because there's so many options out there. I want to just point out ones that are called all-purpose or balanced, and especially when we look at the old gardening guides, they tend to say that those are what should be added pre-plant. And I just strongly encourage you all, especially here in Utah, where we tend to accumulate P and K, you might not need the P and K part of the fertilizers. And so oftentimes you're just looking for one that has a higher first number and lower second and third numbers. Another thing you can do is actually custom make a mix of fertilizers. So you can get N-only fertilizers. My example here is with urea 4600. There's triple superphosphate, for example, is a phosphorus-only fertilizer, and then a potassium-only fertilizer. And so you could weigh each one of those out, make a mix, and then you're applying exactly what your soil needs instead of trying to rely on a pre-formulated mix that has concentrations that might not be relevant to your conditions. Generally, our inorganic fertilizers are more concentrated, therefore you need less. Whereas our organic fertilizers, so this is USDA organic term for organic, those tend to be more dilute. And you need to add more usually. And then there's also this option for green manures, which we talked a lot about in the microfarm session this morning. Okay, so organic nutrient sources, those tend to be quite popular. So I just wanted to touch on those a little bit more. They tend to have lower nutrient concentrations. So thinking about that guaranteed analysis on the bag. But even though they have fewer nutrients or lower concentrations, they can add organic matter, so have an extra benefit. So some of the more traditional options for organic nutrient sources are listed here. They're typically derived from animal and plant sources. And so these are some of their typical nitrogen contents from low to higher. But again, it's not just about the total N. Also think about what's soluble or what's available right away. I've also got a table here looking at different types of manure. So this is an analysis I did on all of the manure samples that came in to the Utah Soil Analytical Lab over the last 15, 20 years or so. So I went through and I looked at average nutrient content for N, P, and K, the pH, as well as the salinity. And right here is, I've just reported the averages, and it goes by animal type. But of course, these numbers range a lot across the different operations, depending on how the manure is handled and so forth. And so this is just a nice kind of estimate for looking at manure types and assessing whether or not they'd be good to add for your situation. A couple of fun ones. So I like to say the ideal manure tends to have more nitrogen than phosphorus and potassium. If you're adding enough manure to meet your nitrogen need, you're probably over applying phosphorus and potassium. So you typically want to add manure to meet your phosphorus need. And then trying to find sources that are closer to neutral and then have a lower salinity. So here, bird-based manures, so chicken, for example, has a really high, so it had the highest salinity in this study. Here's a picture of some chicken manure right here, and the white that's coating the manure, that's actually urine, and that's where a lot of the salt is coming from in these poultry manures. So when I was teaching Master Gardeners a couple of years ago, somebody asked about deer manure, and we had never tested it in the lab. And so I had the Master Gardeners send in deer samples for me, and we got it tested. And to my surprise, it really hits everything that's ideal on manure. It's got a low salinity, pH is near neutral. It's got a lot more nitrogen than it does P and K. And so one night I was hanging out with some friends. One person researches deer and so forth. And I was telling them about this, and we thought, what a great marketing strategy. You could sell Bambi bits because it's just such a good manure source. But anyway, so these are just the averages across the different animal systems. I should note that for dairy, this is just looking at solid dairy manure. Liquid manure was not included in this chart. Okay, running okay on time.
Melanie, just a couple more minutes, probably.
Okay, I've got 2 more slides, I believe, and then a summary. So potential limitations on organic fertilizer sources. Oftentimes, so many of them come with N, P, and K. It can be hard to find N only sources, and also ones that have soluble N. Also, there's concern about the salt content, presence of weed seeds, especially with manure. But that they can help increase soil organic matter. Just be mindful of salt and excess nutrient buildup. I've got a handy dandy equation here to calculate what your needs are based on your soil tests, and a little example here too. So if a soil test says that you need 2 pounds of nitrogen per 1,000 square feet, my question here is, how much fertilizer is that? So for example, if you were to use urea to achieve that, that's a concentrated form of fertilizer. What you would do is take the soil test result, so pounds of nutrient recommended by the soil test, 2 in this case, divided by the number on the bag, that's divided by 100. So 2 divided by 0.46 will give you how many pounds to add. It's about 4 pounds. Now, if I were in an organic situation and I wanted to add feather meal, for example, that's 1200, I would take 2 divided by 0.12, and I'd find that I need about 17 pounds. And again, that gets back at that concentration. It's just not as concentrated, so I'm going to need to add more down to apply. On that fact sheet that I showed earlier, soil sampling for an urban garden, the link is here. I can share that later. We have this nice worksheet as well where you can put in your soil test result and then figure the fertilizer of choice and then figure out exactly how much to add. So with that, the soil is a plant nutrient bank. It's an amazing bank with all these accounts, checking account, allowing the plant to take those nutrients out right away. And we need to replenish what we're taking. When we're gardening and when we're farming, it's a relatively intensive practice to be doing on the soil. And so we need to replenish those nutrients. Getting a soil test helps us understand what the baseline is in the soil and exactly how much to be adding. And then finally, take a look at the label on the fertilizer. Don't over apply if you don't need it. This tends to happen a lot in urban soils. And with that,
Thank you, Melanie.
thank you so much.